Hi guys. Any questions related to the course or labs or anything? Okay, reminder, there's no lab this week. In your timetable, it'll say there is a lab, but there's no lab. And then I think the final abacus assignment is due this Wednesday as well. So from next week, we'll start on ANSYS. So you're welcome to start on the ANSYS labs already if you want as well. And the computers, the new ones are meant to arrive this week. So they've been shipped. So we're just waiting for them to arrive. So hopefully they'll be slowly set up. We'll set them up 1, 2, 3, 4 every day, just filling up that room and then replacing the old ones. Very good. So today I'm going to continue talking about some practical considerations of modern. So a few sets of shorter slides. So we're going to talk about symmetry and then some other topics. Consider the following model. Imagine we have a plate and there's some tension or stress applied, let's say in the X direction, the horizontal direction, and the plate as a whole. So this is like the problem you did in lab 2, this classic Coleman plate problem. So how many planes of symmetry exist? So you might have a symmetry plane in this direction. So everything on the bottom is a reflection of the top, and also there's a reflection there as well. If it was a thick plate as well, you might have a symmetry in the third direction as well. But that's also assuming that the material is symmetric, that it's not like a carbon fiber composite with fibers in some direction. So let's assume an isotropic material. So what can we say about the displacements and stress and forces on the symmetry? So when we want to model using these symmetry conditions in softwares like Abacus and Fluent, what is it actually doing? So it's not actually doubling your model or tripling it and solving it. That's not what it's doing. It's taking advantage of some conditions that we know happen on a symmetry plane, and it just enforces those conditions. So Abacus doesn't know anything about symmetry. It's just enforcing certain mathematical. So look at this point here at the top of the hill, and we're going to apply the loading, and I'm going to accentuate or amplify the displacement. So watch that point. What happens at that point? So we apply a loading. What happens at that point? So let me go back. So that point moved in some ways. So which way did it move, and which way did it move relative to the symmetry plane? Also, I could easily say, look at this point in the symmetry plane. Watch how the point at the bottom of the hole moves. So for this point at the top, you can see, well, it has a y displacement, a negative y displacement, and its x displacement is 0. Whereas this one has a positive x displacement and y displacement is 0. So how can we say this more generally? And okay, I've selected the problem to lie on the y and x Cartesian planes, but I could also run this problem at a certain angle as well. So one condition we can notice, we notice that the displacement in the x direction on this symmetry plane was 0, and equally it was on the displacement on the y symmetry plane is 0 on this other one. So in general, for structural analysis, the displacement in the normal direction, the direction normal to the symmetry plane is 0. So to put that in a different way, if you're a piece of material or a node on a symmetry plane, you have to stay on a symmetry plane. So if you moved off the symmetry plane, the problem is no longer symmetric. So if you have a symmetry plane, you have a piece of material. If that piece of material moves to the right, then you can't have it also on the left as a reflection. That would break symmetry. So for any material that's on a symmetry plane, it has to stay on a symmetry plane. Otherwise, the problem's not symmetric and it's invalid. And so then the normal direction to this symmetry plane, if I say, how do you find the normal this? Sometimes people get confused. They say, well, this is the y direction. That must be y is the normal. But normal means perpendicular. So perpendicular to this y plane here is the x direction. So that would be an x symmetry. A different way to think about that is, imagine the plate is 3D. So it has a certain thickness. So that plane, it would have a normal pointed in the x direction. So the normal displacement, which is the x direction here, is 0, and it will be the y direction will be the normal direction. If you draw a normal perpendicular to that, will be 0. Okay, so any material on a symmetry plane has to stay on it. So that gives us a condition about the normal displacement. So the normal displacement has to be 0. So Abacus is just enforcing that the normal displacement is 0 when we select the symmetry plane. But because this is a 2D problem, you need two conditions. You need some information in the x and y direction. So maybe it's less obvious, but on a symmetry plane, the force in the tangential direction along the plane is also 0. So there's no resistance on a symmetry plane. So when this material wants to slide down this way, the stresses along this plane or the traction along that plane are 0. So why is that the case? Well, if it wasn't 0, then let's say if I tried to pull this material down, it would start shearing this way. So that means something at the symmetry plane will be resistant. But by reflection, the material on the far side would also be resistant. So that would mean that force or energy is being created at the symmetry plane, which doesn't make sense. So if force is equal and opposite, that means that the forces have to be 0. That's the only possible solution for the shear equation. So on this symmetry plane here, the normal displacement is 0 and the tangential force is 0. So there's a 3D problem that force in the z direction will be 0 as well. And equally, you can say that at this plane here. So a symmetry plane, you can kind of think of it as if you had a bearing, a perfect bearing, a roll, say a planar roller bearing that was adhered to the table, and you were holding a plate on that. So if you try to pull against it, it won't let the bearing move away, but it'll have no resistance to moving along the table. So that's all a symmetry, mathematical symmetry plane is doing. So Abacus doesn't know anything about other material or reflecting anything. It's just these conditions are known to hold on a symmetry plane. So when you select symmetry conditions, Abacus is just enforcing those on the nodes. So there are other scenarios that also can be represented using these symmetry type conditions. So that type of symmetry is called bilateral symmetry. So there's two sides. So bilateral symmetry is also known as mirror symmetry or reflective symmetry. And so that's when we think of a symmetry plane, this is like the classic idea of like a mirror. Imagine you bring your part to a mirror, it's a reflection of it. So that's the idea of so-called bilateral symmetry. The displacement in the normal direction is 0, the shear or tangential force or traction is also 0. So when can you use a bilateral symmetry plane? So go back to the mathematical model. What's the definition of a mathematical model? We have some equations, we have geometry, we have loading, and materials. So all 4 of those things have to be symmetric to use a symmetry plane appropriately. So clearly the geometry has to be symmetric. If it wasn't symmetric, if it wasn't a perfect mirror, then if you use a symmetry plane, you're not getting the correct answer. The loading has to be symmetric about the symmetry plane as well. And the material properties. So in the plate problem I gave there, if that was a glass fiber or carbon fiber where the fibers were going at 45 degrees, then that wouldn't be symmetric about the loading direction. You'd have to actually model the whole plate in that case. And then the last one is a little more subtle. This is related to the equations themselves. The solution is expected to be symmetric about the plane. So this one is a little bit more ill-defined. So if we're doing a stress analysis with small deformations, that might be the case, but there are some scenarios where stability comes into play that you may get different solutions that break symmetry. So I won't get you the answer, but maybe just think for a second. Can you think of any case where the geometry, materials, and loading are all symmetric, but then the solution ends up not being symmetric? And I'm not talking about experimental error in here. There's actually mathematically everything's perfect, but you'll get solutions that are not symmetric. That might break symmetry. So there are fluid mechanics. Yeah, go. Perfect. Yeah, buckling. That's a perfect example for, and that's one of the examples I'm going to show. So buckling, you can have something that's a perfectly symmetric, but mathematically the lower energy solution is one that's not symmetric. So the symmetric solution is the higher energy solution, so it's not going to happen. And can you think of other ones as well? There's fluid mechanics ones as well. Okay, so I'll show you some examples, but if you flow over something, say flow over a symmetric object, like a sphere or cylinder, then if the flow is going slowly, then you'll get symmetric flow afterwards. But once the Reynolds number is higher or the flow is higher, then it's not stable to get a symmetric solution. You get a solution that isn't symmetric. You get vortices being thrown off. And that's just the maths, even if it's not due to experimental error in your geometry or anything like that. If you do another if I have a pencil, click down on it, in any direction of equal solution. It will buckle in one direction, and it will just buckle just based on round off error. So if you make a mesh and one of the triangles is a little bit bigger on the other side, then that'll be just enough to break the symmetry, and it'll just click one direction based on your mesh. And that might be computer specific or mesh specific or things like that, precision specific. But sometimes if you know you have a solution that's going to buckle, you may artificially induce a certain direction. So you may purposely apply a small force in the out of plane direction just to encourage it to always buckle in one direction to make the results repeated. And so this is flow around a cylinder. This is one of the problems we're going to look at in week 2, I think, or sorry, the second week of Fluent, whatever week that is, 6. And this is kind of a classic case. So as you increase the velocity, holding everything else constant around a cylinder, initially the solution will be symmetric. So if you see it's okay, it broke the symmetry pretty quickly here, but you can set it up that you get these 2 alternating vortices in the tail, in the wake, like grow longer and longer, but then they become unstable and then they start flicking off alternating vortices, and this is called a von Karman vortex string. So it's like if you put your hand outside the window when you're driving in a car, you feel your fingers wobbling side to side. So that's because vortices are flying off left, right, left, right, left, right of your fingers. So that could be perfectly set up, and we'll set up this problem. I think, yeah, if you set it up perfectly, then the higher the precision of your computer, the longer before the vortex shedding will happen. You need a round off error to throw it off. But I think we set up the problem that's just slightly offset from the top and bottom, so it forces a physical imbalance that, of course, shed. So one thing to point out on that symmetry, on that buckling and that flow problem, if you model that with a symmetry condition, you will get the wrong answer. You will get a symmetric answer because you're forcing symmetry on a solution that doesn't want symmetry. So you have to be careful when using symmetry. So there's other types of symmetry. Bilateral or mirror or reflective symmetry is the kind of classic example. But we've already looked at another type. That was called axisymmetry. So axisymmetric. But there's other types as well. And just be careful, axisymmetry is not the same as asymmetry or antisymmetry, because like they're other things. Okay, just because they start with an A and end with symmetry, they're not the same thing. So just be careful. So what's axisymmetry or axisymmetric? So that's where you have a 3D problem, but it can be represented by its cross section about some axis. So if you have like a pipe or something like that, and if you take a cross section through the walls, if you know what's happening on that cross section, and then you know what's happening everywhere. So you're basically saying the solution is the same on any slice. So it's independent of the circumferential coordinate. So it's only a function of the radial coordinate and the axial coordinate. So it's actually a 2D problem. So axisymmetric problems are 2D. So they're a special kind of class of symmetry where you only have to solve what happens on a slice. And then you know the solution anywhere in the slice is the same as any other slice. It's just rotated around. And then you start to get more and more specialized types of symmetry, which you less often see, and they're more for very specific cases. So there's rotational or cyclic or sectorial symmetry. And then that's where a part of your structure naturally fits into 360 degrees, like an integer number of times, like a whole number of times. So like something like this section here is just repeated all the way around. So in those cases, you can derive conditions that mean you only have to calculate what happens here in one of those sectors, because the same thing happens in all the other sectors. So for example, in turbo machinery, if you're designing turbines, you might only simulate what happens around one of the vanes, and then you can average to get what happens around all of them. And then some other specialized type, translational symmetry. This is where you have some repeating structure, which is just, you have an array of parts that are all connected together. So this type of analysis might be used for microstructure analysis. So if you're analyzing the microstructure, let's say imagine this is a cross section of a composite, so a carbon fiber composite, and these are the carbon fibers. This is the epoxy resin. So in that case, you might want to derive the mechanical performance of the microstructure in some way. So you might just simulate a representative element, and then you know that this is beside another one, which is beside another one, which is beside another one, and they're on top of each other. So when you load them, and they don't stay flat, the sides, but it's basically whatever happens on this side is just transferred to be applied on this side. So it's like symmetric without the top and bottom or left and right. So once again, these are kind of specialized type of analysis, but it's another type of symmetry. And the last one, which you may have seen in Abacus already, and when you go to select boundary conditions, you'll see X sim, Y sim, Z sim, but there's also AX sim and YX sim, so anti-symmetry. So this one's a little bit stranger, but imagine we set up a problem like this. This is a 4-point bend. So I have some supports here. I apply a load there and there. My material I assume is isotropic. I have a bilateral symmetry plane here. So we can use just a classic symmetry plane here. The X displacement will be 0, the Y force is 0. But what happens if I actually apply the load in this direction? So it's almost the same, it's just the loading is in the flipped exact opposite direction, not in a random direction, just in the exact opposite, like pushing instead of pulling, tension instead of compression. So that specialized case is called anti-symmetry. You can derive, it's like the opposite happens at the symmetry plane. So instead of the normal displacement being 0, the tangential is 0. Instead of the tangential force being 0, the normal force is 0. So that's called anti-symmetry. But to be honest, most of these, unless you go into a very specialized area, you won't use. It's just a reflective symmetry, mirror symmetry. So why use symmetry? Just one is efficiency or speed. So if you can half your problem or quarter of your problem, it'll be at least twice as fast, 4 times as fast. So let's say if we use one bilateral symmetry plane, that will be half the number of nodes for the same mesh resolution. So typically that would be more than twice as fast, because how long it takes to solve simultaneous equations isn't linear. It's worse than linear. So if you double your number of nodes, it won't take twice as long. It could take 2.4 times as long. So if you half the number of nodes, it will be at least twice as fast. So that's one reason. Another reason we talked about is rigid body constraints. So if your part's going to float away, you can use a symmetry plane if it is symmetric, and then you don't have to worry about your part floating away and causing singularities in the matrix, etc. Commonly, based on my previous experiences in this course and elsewhere, people will say, my problem's too small, I don't need to use symmetry. It's so quick to run anyway. So that may be true, but typically then if you don't use symmetry for small cases, then when you have a really big problem, then you won't trust yourself that you're using it correctly, and you may be using it incorrectly if you have practice using it. So I would suggest to use symmetry in all cases where it's relevant. And then my manager won't understand it. So that's not true. People understand symmetry. It's not that complex a topic. In any case, Abacus and other softwares can mirror your results. So if you do a symmetric problem, in one or two tutorials I think I showed, you can just reflect it, or if not, I can put up some instructions. When you have your results, you can just turn on an option in the visualization that just reflects the results, so you see the full results anyway. So that's not a problem. All right, quick symmetry. Any other comments or questions on that while I open the next one up? Okay. Okay, so the next set of slides I'm going to talk about is related. It's similar to rigid body modes, but it's called zero energy modes. It's a little bit more non-intuitive, but I think you'll understand it. So zero energy modes. So let's go back and look at this problem before, where we have a block with a force being applied in the two different directions, or the x and y, or the positive x and negative x direction. And in this case, the part will contract in the y direction and elongate the x direction. So when we looked at rigid body modes, as in just rigid translation, those motions or deformations did not cause strain in the part. So when we rigidly move this part from here to here, the strain in the part doesn't change. The stress in the part doesn't change. You're just rigidly moving it to a different place. So that's what we meant by a rigid body mode. So it didn't change the strain or the strain energy in the part. And if those rigid body modes were not constrained properly, like you let the part fly away, then they can all snowball, and then your solution procedure will fail and won't be able to solve it. Try to use very small time steps and just something that won't work. So a similar concept are called zero energy modes, and this is a numerical artifact. So some finite elements, so let's say we replace that block by a quadrilateral or square element with 4 nodes. So some finite elements can deform in non-rigid ways as they change shape, but produce no strain in the element. So if that can happen, then it's like a rigid body mode. So let's see an example of that. So these are called spurious zero energy modes. And so when we look at square or quadrilateral elements in abacus, there are 2 types. The default is called a reduced integration type. So in reduced integration, you have your 4 nodes where reduced integration is just one point central of the element. So the strain and stress are calculated here, whereas the 4 nodes on the edge are where the spaces are. So when you tick off reduced integration, it'll use full integration. So in that case, it'll actually calculate the stress and strain at 4 points. And the coordinates of these are given by Gaussian quadrature, which we're not going to go into the details of. So let's take the default element in abacus, and let's apply that loading case that I just told you about. So I apply this uniaxial loading. So it extends in the x and y direction. Let's imagine that rigid body modes is not a problem here, that's not drifting away. So it's forced to stay about the center. So it contracts in that direction and gets longer in that direction. So how do we calculate the strain in the element? Well, we can go back and check our functional form, and we can do our derivatives, and then we have an actual formula for the strain tensor as a function of the nodal displacements. We can do that, but I'll just skip over that and just show you the answer it gives you. And actually, you can intuitively get to the same answer anyway by looking at the problem. So the strain in the x-x direction for this element is just the change in length in the x direction by the original length in the x direction. Okay? So delta L over L. So this delta x is just the original length in the x direction of the element, and this delta D or delta actually using is the change in displacement in the x direction. So if I say, well, what's the change in displacement in the x direction of this element? So I'll say it's D1 and D2. If I take the average of both of their displacements, that's the displacement in the x direction there. The average of 4 and 3 in this direction is the displacement in that direction. So if I say the average of their displacements minus the average of those, that's the change in displacement, divided by delta x is the original. So the average of these 2 displacements minus the average of these 2 divided by the original distance. So actually, if you plugged in our functional form and did all those calculations, you'll actually get the same formula. This is just deriving from physical principles. So if you do that, now imagine that we artificially deformed our element into this shape, like a trapezoid. And I purposely decided to make D1 to be equal and opposite that of D2 or delta 2. So like that might be -1 and this is +1. So that means the average of both of these displacements is 0. So like at the center of this edge, the displacement is 0. The average of D1 or delta 1 and delta 2 is 0. And similarly, the average of delta 3 and delta 4 is 0. So I purposely chose that displacement field or that type of deformation. So if this element deforms in this trapezoid shape, and we ask it, what is your XX displacement? It will say 0, because the average change in length in the x direction and the y in the x direction is 0. So if you look at the midpoints of these elements, you can see they didn't change length. So for this type of deformation, the average XX strain is 0. So this type of deformation, and by type of deformation, we can call that a mode of deformation, a way it changes shape. This mode of deformation produces no strain in the element. So that's like a rigid body mode. It's like moving it rigidly. It's not generating any strain or strain energy. So if you move the element, somehow you go in and just say poke it like that, it will not resist that because it doesn't have any stiffness in that direction. It doesn't produce strain in that direction. It'll just let you move it that way, and then it'll just stay in that direction. So 2D quadrilateral linear elements, reduced integration, they can undergo deformations that do not produce strains or stress. So that's a bad thing. That's not physical, right? And that can happen. So that is one type of what's called a zero energy mode or a zero energy deformation. And if they appear in your model, if the elements start doing that when you're using these elements in your model, they typically won't go away. They'll just stay there, and they will pollute or destroy the solution. So your answer might end up being nonsense, or you just kind of have this garbage in your model that makes it not very useful. So when you make assemblages of these types of elements, you put them all together, then there's certain modes of deformation of the overall finite element mesh that are permitted and that produce no strain. So essentially, if you have two elements on top of each other, if the bottom one is trapezoid this way and the top one's a trapezoid that way, then both of those will have zero strain. So this type of zero energy mode is called hourglassing. So this is a particular type of zero energy mode. There's other types of zero energy mode, but this is a particular type that you might see in abacus. So if you look at your overall mesh, you'll just see it goes in, out, in, out, in, out, in, out like this. And it's called hourglassing because it looks like an hourglass, like it does little sand tiny things. So visually, this looks like an hourglass, and they often call this hourglassing in finite element literature, and they call it hourglassing in abacus. So if you see hourglassing in your model, you need to be careful. You need to do something because it's just nonsense, essentially. So what happens if we turn off that reduced integration switch and we use fully integrated elements? And well, in fully integrated elements, you're calculating the strain here, 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 and here. So the strain will be the average of those. So in those cases, because you're calculating strains in multiple places in the elements, they don't permit hourglassing. So fully integrated elements will generate a strain if you try and move them in an hourglass mode. So they won't allow that. It won't be a zero energy mode. So they'll like, unless that's a physical deformation, they won't start doing that with no energy. And similarly, if we just look at 2D triangular elements or triangles, they won't suffer from hourglassing either, because there's none of these modes that you can create that will permit zero strain. There's no way to move a linear triangle that changes its shape that doesn't produce a strain. So when we're using triangles in our derivation that we went through, that won't be a problem. It's only when you get squares or less simple element shapes. So that applies in 2D, but it also applies in 3D. So tetrahedra is a triangle-based pyramid. That's the equivalent of a triangle in 3D. They don't suffer from hourglassing. But for hexahedra, which are six-faced blocks like cubes, they will suffer from hourglassing if you're using reduced integration. Whereas if you're fully integrated, it won't. So how do you avoid this? These zero energy modes, because they're bad and they can destroy your solution. So by default in abacus, they use something called hourglass stabilization. So this is just turned on by default because obviously they don't want hourglassing to occur. So this is where they create artificial stiffness terms. They're added to the stiffness matrix. They basically take the stiffness matrix of the element and they start adding numbers in that aren't physically there for any reason. It's just to try stop the element moving in that direction. So that can work okay. It can quell those zero energy modes, but it tends to make the elements less accurate. So it's kind of like they're smoothing, they're adding like a smoothing term to stop the elements being so deformable. So it is a balance and it's hard to get that right. It's a bit ad hoc, but this is what's used by default and it works okay, but sometimes you will still get zero energy modes. But sometimes it doesn't work. And if you go to the element formulation in Abacus, the element controls, and you can switch between linear and quadratic or reduced integration, fully integrated, so other options. You'll see a section called hourglassing there. So you can click on something called enhanced hourglass control. So that's just another formulation of hourglass stabilization, more aggressive. So it will add more terms or larger terms to your stiffness matrix to make it less susceptible to hourglassing, but at the expense of lower accuracy. So that's why they don't turn it off by default. So I set up a problem in Abacus just to show you, and you can try this. So I just made a square. I use some symmetry planes on the left and right. As we know now, symmetry planes is just constraining the displacement x direction, no force in the y. It isn't actually modeling symmetry. And zero displacement at the bottom. And I applied a point node to one node here. So point load as well, okay, I'm creating a singularity. But because applying point loads are a great way to amplify zero energy modes. So that's like the worst case scenario. If I push in just one node, it will tend to excite these modes. So if I do that with the default elements in Abacus, you get a solution that looks like this. So what you would expect the answer to be is just you get a depression, the material bends down, you have a higher stress here, and it varies away. But if you look here, you can see all these little hourglasses that they're going in and out, like an accordion shape everywhere. So that's classic hourglassing. So if you ever see your elements going like that, and you're not sure if it's physical or not, well, one, it's probably is artificial. But if the motion of your elements or the way they deform is exactly the frequency of the elements, it's more likely than not an artificial thing. So if you're not sure, change the mesh. And if it's still the frequency of the mesh exactly, then it's probably the mesh. It's not the underlying material. So there are the default reduced integration elements. So if I go to the element controls and I turn on enhanced, this more aggressive stabilization that reduces the accuracy, then it actually does stabilize this problem. So this displacement field is reasonable. This is closer to what you might expect to happen. So in this case, enhanced stable hourglass control will solve the problem, and you start getting reasonable answers. Alternatively, I could run it with full integration. So if I just turn off reduced integration, then it becomes fully integrated. Since I have a fully integrated element, you can see hourglass control is not an option because you don't need hourglass for fully integrated elements. And then I also get a reasonable answer. So the answers are almost the same. I think I'm not sure if I was using the same scale here. Also, if you go to quadratic elements, it depends on the formulation. Quadratic elements fully integrated won't hourglass. The quadratic reduced integration, I'm not sure if they will or not. I think they don't in this case. So it depends on the formulation, depending on your element type and shape. But it's certainly something to be careful of, to be aware that those types of problems can happen and that they're a purely numerical phenomenon, not a physical. So how do we avoid zero energy modes? You can use fully integrated elements. And if they don't suffer from it, why does Abacus not just use those by default? Well, when we saw from the plate hole problem, the fully integrated elements are actually just a little bit less accurate than the displacement, than the reduced integrated ones in general. So they trade off. They say we'd rather have more accurate elements, and then people can turn on stabilization if they need it. Or you can use alternative formulation, higher order. By higher order means more than second order, so like quadratic elements. Or there's other formulations we're not going to go into, like hybrid elements. There's all these or incompatible mode elements. There are different formulations of the elements that can avoid these problems. Oh, it's the last slide. There are some other types of zero energy modes. So hourglassing is one type. But if you're modeling incompressible or almost incompressible materials, you can get pressure checkerboarding, which is a type of zero energy mode where you get spikes up and down in pressure as well. So there are some other types as well. So the next set of slides I wanted to go through, I know it's 41, but I might just start. And then we can finish in the next slide just to get you thinking about some of the concepts. So the next set of practical considerations, I think these are my last slides of practical considerations. So it's about mesh generation. So mesh generation, one of the main disadvantages of the finite element and finite volume meshes is how long it takes to set up meshes. This is often the part that you spend way more time on than anything else. Pressing go and letting the model run and going off and getting coffee is easy. Like, if the model takes a week, that's fine because you probably spent a month creating a mesh. So this is actually a mesh from my PhD. So I was working on a hip joint model. I must have spent months and months, 6 months on this. It was really painful. It was I learned a lot, but it was very, very painful. So I looked at loads of different ways to make meshes of complex parts, accounting in this case for there was like cortical bone and calcaneus bone, different stiffnesses, cartilage, varying thicknesses, and there's all these different element formulations. And then you can make certain element types, and then you bring it in software, and it just wouldn't converge because they weren't well formulated. They were like poor elements. So it's a real pain, and it's a major bottleneck in finite analysis. And there are people looking at alternative approaches, so-called mesh-free approaches to avoid this. But mesh generation can often be the slowest part of the overall workflow. And that's a major bottleneck. But let's just, in these slides, go through some of the approaches to making meshes and classify them, and then talk about their relative merits of why you might use one rather. So if we take our lovely hole in the plate problem, and let me show you a mesh for this. So here in this mesh, I've actually used 4 separate meshing approaches. So you'll naturally see there are different shapes. So we have quadrilaterals, 4-sided shapes, and triangles. But also you can see they're arranged in different ways. So if I ask you to classify the types of mesh, you might say here, we can say, well, you have triangular meshes and quadrilateral meshes. That's 2 ways that's one way to classify them. But also the way they're arranged. So you can see this bottom left corner here, it's arranged in grids. There's like repeating structures. Whereas over here, it kind of looks like someone's doing a paving your driveway or something like that. It's like someone just started putting little blocks down. So they just start on one side and then they just start filling in those blocks. And then similarly over here, this one's kind of structured triangles, and then this one's a little bit more random. I'm not going to do that whole EV now, but I think I'll just leave it there as a good place to stop, and then we can go through some of these. Great, see you on Wednesday.